Good morning, students. In this video lecture, we are going to discuss about the complement arithmetic. Before that, we will discuss how to represent the negative number in ones and twos complement. Actually, we have three representations for negative numbers. First one is called sign magnitude form. Second one is ones complement, and third one is twos complement. Sign magnitude. If we want to represent the number in sign magnitude, then the MSB should indicate the sign, only one bit. Why? Because we have either positive or negative number. So one bit is enough to differentiate these two. If the MSB is 0, then that's a positive number. If the MSB is 1, then that's a negative number. So suppose I want to write -7 in 4-bit format. Then I have to use 1 to indicate it's a negative number, and I have to use the remaining 3 bits to represent the binary equivalent for this -7, that is 1 1 1. So -7 is equal to 1 1 1 1. Suppose I want to write the same -7 in 8-bit format. Again, to indicate it's a negative number, the MSB has to be 1. This is indicating it's a negative number. The value of 7 is 1 1 1, but totally we have only 4 bits. We want to represent this in 8-bit format, so we have to write this 7 in 7-bit format. Instead of using 3 bits, now we need to use 7 bits. So what we have to do? We have to insert leading zeros. So that will become, the representation is like this: 1 followed by 1 2 3 4 zeros followed by 111. So here we have 7 bits for the value, and of course the value is 7, and the 1 bit is allocated for sign, that one is minus. So this is equal to -7. How to represent +7? Simply change this as 0. Then that will become +7. So this is sign magnitude representation. We have 2 more representations. These are widely used in our digital system. Ones complement and twos complement. In ones complement, to write a negative number in ones complement, first we have to write the unsigned representation. For example, let's take again -7. The unsigned representation of 7 in 8-bit format is 0 0 0 0 0 1. This is the unsigned representation. This underscore is to see the bits clearly. Here I have 4 bits. Here I have 4 bits. Actually, in your examination, no need to put this underscore. If you are putting this underscore, that is well put, right? To obtain the ones complement, we need to invert each and every bit. That means this 0 should become 1, 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 and then this 0 should become 1, this 1 should become 0, this 1 should become 0, this 1 should become 0. This is the ones complement representation of -7. What is the ones complement representation of +7? That is the unsigned form, this one. So there is no difference in bit patterns for positive numbers. The positive numbers are given, are represented the same manner in all 3 representations: sign, magnitude, ones complement, twos complement. In all 3 representations, +7 is represented as 0 0 0 0 0 111. This is the 8-bit pattern of +7 in sign magnitude. This is the 8-bit pattern of +7 in ones complement. This is the bit pattern, 8-bit pattern of +7 in twos complement. There is no difference. The difference comes only in negative numbers. So only here we have the pattern for negative numbers. And you can see the MSB. If the MSB is 0, then it is a positive number. If the MSB is 1, then it is a negative number. If it is a negative number, then only we have to check whether it is represented in sign magnitude or ones complement or twos complement. If MSB is 0, no need to check that one. Why? Because in all 3 representations, the bit pattern will be same. So this is the ones complement representation of -7. How to obtain twos complement? To obtain twos complement, obtain 1's complement and then add a 1. The answer will be 1 1 1 1 0 0 0 1. This is the 2's complement representation of minus 7. So minus 7 is represented as 1 followed by 4 zeros and then triple 1 in sign magnitude. 1 2 3 4 5 1 and then triple 0 in 1's complement. 1 2 3 4 4 zeros, sorry 4 1 followed by triple 0 followed by a 1 in 2's complement. So see the bit patterns are different in these three representations if the number is negative. That's important. If the number is positive, then the bit patterns will be same. So this is the way to obtain the 1's complement and 2's complement of the negative numbers. 1's complement and 2's complement are used widely, so pay attention on this. Sign magnitude is simple. We have to write the unsigned form in n-1 bits. By using n-1 bit, the MSB should be either 0 or 1 according to the positive or negative sign. Now here we have the definition. In sign magnitude representation, MSB indicates sign, that means 0 for positive, 1 for negative, and other bits represent the value. In 1's complement, write the unsigned bit pattern, invert each and every bit. Suppose if you are asked to write in 4-bit format, you have to write the unsigned bit pattern in 4-bit. 8-bit means we have to write the unsigned representation in 8-bit. How to write the 8-bit pattern for 3? We know how to obtain the bit pattern. 1 1 and again 2 means 0 1, quotient becomes 0, so this is our binary 1 1. But I want to write this in 8-bit format, meaning I have to add 6 zeros in front. 0 0 0 0 0 0 1. This is the 8-bit format of 3. What is the 4-bit format of 3? 1 1, but we need 4-bit, so include 2 zeros. How to write the 12-bit format? 1 1, 10 more bits are needed, add 10 zeros. 4 8 10. This is the 12-bit format of 3. So first write the unsigned bit pattern by using for the given number of bits, and then invert each and every bit. That one is 1's complement. 2's complement, obtain 1's complement and add 1 with the LSB. So here we have some example how to represent minus 5 in these three format. Sign magnitude, 1's complement, 2's complement, if the number of bits are 4. See here I have 4 bits, 4 bits, 4 bits. First I have written the unsigned representation of 5, that one is 1 0 1. 4 bit means I got to add 1 0. Sign magnitude, this should be 1, so 1 1 0 1 is coming. 1's complement means each and every bit should be inverted. 1 0 1 0, that one is available here, 1 0 1 0. 2's complement means I need to add 1 with 1 0 1 0, that then I will get 1 0 1 1, that one is available here. 8-bit format means MSB should be 1 and we have this value 1 0 1, the remaining bit should be 0. 12-bit format means MSB should be 1 and this is the value for 5, the remaining bit should be 0. This is sign magnitude. But what we have to do for 1's complement? Once you obtain this for 4-bit, if you want to extend this one for more number of bits, add 1 the left hand side. So that one is called sign extension. You will study this in your computer application later. Sign extension. Meaning, suppose if you have one number 0 1 0 1, this value is plus 5. You are asked to extend this one, or you are asked to write plus 5 in 8-bit format. This is sign, right? That sign should be extended for the remaining bits 0 0 0 0 0 1 0 1. This is plus 5. In 12-bit format, now this is sign, right? That sign has to be extended 0 0 0 0. So this is the 12-bit representation of plus 5. What is the 4-bit representation for minus 5 in 1C? 1's complement. That one, just now we found that one as 1 0 1 0. What is the 8-bit representation of minus 5? See, this is sign. That sign should fill the remaining bits. 8-bit means I need 4 more bits, so I have to add 4 ones. Suppose you are asked to represent this in 12-bit format. You have the 4-bit format of minus 5, 1 0 1 0. Now 8 bits should be added. The 8 bit should be the sign. 1 means 8 1 should be included, so that the value will be changed. So if a sign is 0, 0 should be extended. If a sign is 1, 1 should be extended for the remaining bits. Of course, you can find the unsigned representation and then you can invert, you will get the same answer. If you remember the sign extension, you can easily get the 1's complement of minus 5 in 8-bit format and 12-bit format. See, the sign is extended. 2's complement, 4-bit format means first we have to write the unsigned representation of this one, and then we need to take 1's complement. 1's complement equal to 1 0 1 0. For 2's complement, we need to add 1 is LSB, so value is 1 0 1 1. This is the 2's complement representation of minus 5 in 4-bit. That one is given here. If you want to write that in 8-bit, see, the sign is 1, so 4 ones are added before this one. If you want to represent minus 5 in 12-bit format, 4-bit format is this one, the sign is 1, so the sign is extended for the required number of bits. Here I need 8 more bits, so 8 ones are preprinted. So in this way we can obtain the 1's complement and 2's complement binary representations of negative numbers. Here some examples are given. Just go through this. Range of an n-bit binary number, sign magnitude minus 2 power n minus 1 minus 1 to plus 2 power n minus 1 minus 1, and the 2 representations for 0. One is 1 followed by all 0, the second one is 0 followed by all 0s, n minus 1 zeros. 1's complement, same range. Here also we have 2 representations for 0. 2's complement, we have only 1 representation for 0, so the range is minus 2 power n minus 1 to plus 2 power n minus 1 minus 1. Right. Now let's see the addition and subtraction in complement form. Subtraction is carried out by using adders alone. Subtractor is not used to do subtraction if the binary numbers are in complement form or represented in complement form. So remember, subtractor is not used. Then how to perform subtraction? Subtraction is performed by using adders. Subtraction is performed by using addition. How to perform addition to do subtraction? See this one. Suppose you want to subtract b from a. This is subtraction, a minus b. That one is done by adding a with minus b. Meaning a minus b can be written as a plus minus b. We have to write the binary pattern for a and we have to write the binary pattern for minus b, and these two should be added. Similarly, if you want to subtract minus b from a, meaning we want to perform a minus of minus b. That one is performed by the operation a plus b, minus into minus plus, right? So a plus b, what we have to do? We have to write the binary representation for a and we have to write the binary representation for b. These two should be added. So only adder is used to perform both addition as well as subtraction. Right? We can do this by using 1's complement or 2's complement, right? If you want to perform the addition by using 1's complement, if carry is produced, we are going to add, right? Carry may be produced, carry may not be produced. If carry is produced, then add it to the sum. Carry may be either 0 or 1. If carry is 0, 0 should be added. If carry is 1, 1 should be added. Add it to the sum. You will get another result, right? That is the correct result. If carry is produced, the actual sum should be incremented by 1. When doing 2's complement addition, if carry is produced, ignore the carry. Don't bother about the carry. So this is a simple operation. When performing addition, the carry may be produced. If the carry is produced, if you are doing in ones complement, then the carry should be added to the LSB of sum. If you are performing the addition in two's complement, ignore the carry. Simple. After doing this one, check your MSB. If your MSB is 1, then that is a negative number. The result is in complement. So to know the actual decimal value, we have to take another complement. A complement is true form. If our MSB is 0, then the value is positive and the number is given in an unsigned representation. We can use the binary pattern to find our decimal. So let's see some example. We want to perform 2 plus 5, 2 minus 5, minus 2 plus 5, minus 2 minus 5, minus 2 minus 6 by using ones complement. First let's take 2 plus 5. Here we have the ones complement. We want to perform this one in ones complement method, right? So here we have the ones complement representation for plus 2, plus 5, minus 5, minus 2. These four are going to be used, right? Of course, we have minus 6 also. We will discuss that one later. Plus 2 is 0, 0, 1, 0. Plus 5 is 0, 1, 0, 1. Minus 2 is 1 complement 1, 1, 0, 1. And minus 2 equal to 1, 0, 1, 0. And students remember, by using ones complement, we can represent minus 7 to plus 7 in 4-bit font, right? Minus 8 is out of range. To show you what will happen if you try to obtain minus 8, I have taken this example. Minus 2 minus 6 is minus 8, right? Similarly, plus 8, plus 9, plus 10, etc., etc. These are also out of range. Here minus 8, minus 9, minus 10, etc., etc. These are also out of range. So if you have two numbers to produce the out of range, then that one is considered as overflow, meaning you won't have the correct result. That is not possible. Right. Now I have written the ones complement of plus 2, that one is 0, 0, 1, 0. Ones complement plus 5, that one is 0, 1, 0, 1. Perform addition. Always perform addition. 0 plus 1, 1, 1 plus 0, 1, 0 plus 1, 1, 0. And see the MSB is 0, meaning it is a positive number and it is represented in true form. So our value is equal to plus 7. 0 triple 1 is plus 7 more. Right. Now let's see the second example. 2 minus 5. 2 is 0, 0, 1, 0. Minus 5 is 1, 0, 1, 0. That one is given here, right? Minus 5 is 1, 0, 1, 0. So I have written the ones complement of minus 5 and then I am going to add. Meaning to perform 2 minus 5, I am doing 2 plus minus 5. I am writing the binary pattern for 2 and I am writing the binary pattern for minus 5 and then I am adding. 0 plus 0, 0, 1 plus 1, 1, 0, 0 is here and 1 is going here. 1 plus 0 is 1, 0 plus 1 is 1. And this one is our result. No carry is produced. So no need to add that one with this LSB. Now check your MSB. MSB is plus 1. So it is a negative number and it is available in ones complement form. To know the actual decimal value, we have to take again a ones complement. 1, 1, 0, 0. If you are taking ones complement, that will be 0, 0, 1, 1 and it is equal to 3. So 2 minus 5 equal to minus 3. Why minus 3? Why? Because MSB is 1. So this is the answer. Now let's see the third problem. Minus 2 plus 5. Minus 2 is 1, 1, 0, 1. What is 2? 2 is 0, 0, 1, 0. So minus 2 is 1, 1, 0. That one is written here. And plus 5 is 0, 1, 0, 1. If we add this one, 1 plus 1 is 1, 0. So 0 is available here. 1 is coming here. 1 plus 0 is 1. And 1 plus 1 is 0 again. And 1 is coming here to the fourth bit. 1 plus 1 is 1, 0. That 1, 0 is given. See here we have a carry. This carry has to be added with the LSB. If the carry is added with that LSB, actually we are having this addition 0, 0, 1, 0. This is our sum. Here I have a carry. This carry is coming here. And then we are adding that one, meaning we are getting 0, 0, 1, 1. The carry is coming here and it is added with the sum, right? So this carry is also called as end around the carry. end around carry. Right. So now our result is 0, 0, 1, 1. Check the MSB. MSB is 0, meaning it is positive and it is given in a true form. The answer is plus 3. Now the last one, minus 2, minus 5. Write the ones complement representation for minus 5, that one is 1101. Ones complement representation of minus 5, that is 1010. If you are adding, we are getting this result. As we have a carry, we have to add that one with this one. And our result is 1 followed by 000. And check your MSB. MSB is 1, meaning it is a negative number. To know the correct value, we have to invert this. If we invert, we are getting this one, 0 followed by 111. 0 followed by 111 equal to 7. So the decimal equivalent for 1000 is minus 7. And that is the answer. So this is ones complement arithmetic, subtraction or addition. Hope it is clear. And I request you to choose some other examples and try. Right, let's see the last one. Last one is minus 2, minus 6. The ones complement representation of minus 2 is 1101, since plus 2 is 0014. So minus 2 is 1101. Minus 6, the unsigned representation of plus 6 in 4-bit format is 0110. So the ones complement is 1001. Now add 1 plus 1 is 10, 1 is going here, 1 plus 0 is 1, 1 is coming here 1, 1 plus 1 is 10, this one is called as carry, right? This carry is going to be added with this one, so we are getting the result 0, 111. This is our result. So, and see our MSB. MSB is 0, meaning it is a positive number. And if we calculate the value equal to 7. So, our answer is like this, minus 2, minus 6 is plus 7. This is our answer. But we know the answer is wrong, right? So, this is called as overflow error. Overflow error. Why it is called as overflow? Why? Because by using 4-bit, we can go from minus 7 to plus 7 only. But the sum tries to produce minus 8. Minus 8 is out of range, overflow. So this is called overflow error. Right? How to find overflow error? See, here the sign is 1. Here the sign is 1. If you are adding equal sign numbers, then the result should have the same sign. Overflow will occur when you are adding two positive numbers or two negative numbers. If you are performing plus minus or minus plus, at the time overflow won't occur. So when both operands are having the same sign, the result should have the same sign. Otherwise, the result is wrong. That one is called overflow. In computer organization and architecture, you might have hear the term overflow. See, there is a difference between carry and overflow. Carry and overflow are not same. Don't think I have only 4-bit, but I have 5-bit result. So the 5th bit is overflow. That 5th bit is called carry. That one is not overflow. So this is a carry. The 5th bit is carry. And the carry is used, right? But when you are adding two signed numbers, and if the both data have the same sign, and the result is having an opposite sign, then that is considered as overflow. See, this is the 4th bit. So here we don't have carry. This is 4th bit. The 4th bit has a different sign. Carry, what is carry? Carry is the 5th bit. Carry will be saved in a flag called carry flag. So if you want a complete result, the sum is going to be appended with carry. This carry will be saved. Suppose you are using 4-bit registers. Register A 4-bit, register B 4-bit, and you are saving the result in A, meaning you are writing like this, A equal to A plus B. So this is 4-bit, this is 4-bit. While adding two 4 bits, the result may have 5 bits, but A has the capacity to save only 4 bits. So the last 4 bits are saved in A, and the fifth bit is saved usually in a carry flag. Carry flag is a 1-bit register. So at the time of taking our answer, we will take the answer along with the carry flag. Here we have either 0 or 1. Here we have the remaining 4 bit. So carry is needed, necessary. Overflow indicates error. Carry doesn't indicate error. Carry is part of the answer. Hope you understand. Okay students, let's stop here. In our next video lecture, we will discuss about 2's complement arithmetic.